Hey guys, welcome back to Solutions. In part 2 of this unit, we're going to be talking about the solution process and factors affecting solubility. Let's get started. Okay, so the solution process has several things that are happening. These are the energy considerations that we're looking at. First, we've got the solute. So if we, let's say, had salt water, that'd be between the salt and the salt. So you're breaking ion bonds or IMF between solute particles, expanding the solute, and this is an endothermic process. The reason why it's endothermic is endothermic equals bonds breaking. You have to put energy into the bonds or the IMFs to get them to split apart. Then we have the solvent. So if we had salt water, this would be water. So you're breaking the IMF or the bonds between the solvent particles and expanding the solvent. And this is also an endothermic process because bonds breaking is endothermic because you have to put energy into the bonds to get them to break. And then we have the solute-solvent. So if we're talking about salt and water, this would be between the salt and the water. The solute and the solvent interact to form intermolecular forces, and now we have an exothermic process. Exothermic, that is bonds forming instead of breaking. Bonds forming is an exothermic process. Whether a dissolving process is endothermic or exothermic will depend on the magnitude of each one of these factors. But every time you've got dissolving, you've got all three of these things happening. So here's a picture of how this might work. So our first one, and I'm sorry this picture looks a little funky, is the solute has got to expand so the solvent can fit between the molecules. And the solvent has got to expand so the solute can fit between the molecules. So this is the endothermic bonds breaking processes happening. And then once they've both expanded, then you have the solute and the solvent coming together to make an entire solution. So really, the way we see it when I put salt in water, what I'm going to see is I'm going to see the salt dissolved in the water and the water with salt dissolved in it, and it's going to look like all one thing is happening. But really, we have three processes going on. We have the two endothermic processes of bonds breaking apart or IMF weakening to fit the other thing in, and then we have the exothermic processes of bonds forming or intermolecular forces forming between the solute and solvent. So in the box below we're going to draw a representation of what magnesium chloride would look like after it's dissolved. So notice that magnesium chloride is an ionic compound, so they're not actually connected together. They're held together by the electrostatic opposite charge attractions of the positive and negative ions. But in the water molecules, they're covalently bonded, so they are attracted or attached to each other by those covalent bonds. So let's zoom in on this picture and try to make it right. So here's my after dissolving picture. So I'm going to have those, let's say a +2, I'm just going to write a +2 for my magnesium. And my water is going to be blue. And I've got like a little Mickey Mouse with a negative oxygen and a positive hydrogen. And there's another little Mickey Mouse with a negative oxygen and positive hydrogens. And then we've got the chlorine. That's going to be bigger, and that's a negative charge. And again, we've got a water molecule with positive hydrogens. Notice the positive hydrogens are facing the same way as the negative chlorine, and the negative oxygen is facing the opposite way. So let's put another +2 in there, and we're going to put some more water molecules in there. These are my really bad pictures of water molecules here. That one just was too big to be allowed. Let's try it again. You guys, I've got a load of my really bad handwriting Okay, there's a negative, there's another chlorine minus, here's another chlorine minus, and, well, at least that's 2 magnesium chlorides, all surrounded by waters. Notice the positive hydrogens are attracted to the negative chlorines, and the negative oxygens are attracted to the positive magnesiums. Well, those should be connected. Let's see, that one also just can't be allowed. Let's try it again. Okay, so we're going to end up with something kind of like that. So that's what it should look like after it has dissolved. So factors affecting solubility, this is why something may or may not dissolve. We are going to consider 3 things. The first one is structure effects, as in the structure of the molecule, or the type of bonding present in the solute and the solvent. So the phrase that we commonly use that the College Board doesn't really appreciate is like dissolves like, which means that things with similar type of bonding are soluble in each other. So polar things dissolve polar and ionic, and nonpolar things dissolve nonpolar things. So here we have some pictures of a lot of the IMF that we talked about in our previous unit. So the first one we have is London dispersion forces. This is a nonpolar heptane and a nonpolar pentane. And the London dispersion forces, or induced dipole, are the types of IMF here that would be interacting. And then the other 3 we have dipole and ion dipole. So notice that the negative end of one molecule and the positive end of the other molecule are attracted to each other. So we have 2 polar molecules, and we have acetone and chloroform, or ethanol and water. Again, the negative end of one molecule is attracted to the positive end of another. This is hydrogen bonding because we have the oxygen right there and the hydrogen in white. So we have an H bonded to an O on one molecule, an H bonded to an O on another molecule, and then they're attracted to each other. And then, of course, we have the ion dipole, which we were just doing earlier with magnesium chloride. Here is an Na plus ion surrounded by these negative oxygens. So this is our ion dipole forces. So here are some examples of structure effects in action. First of all, will CCl4 dissolve in water or bromine, and why? So we got to know the shape or the structure of CCl4. And hopefully you can draw this guy pretty quick and recognize that he's a tetrahedral shape. And remember that tetrahedral shape is completely symmetrical, which means CCl4 is nonpolar. Now let's contrast that to water or bromine. So if I draw water, there's my water molecule. And although it looks symmetrical, remember that water molecule with those 2 lone pairs? Those lone pairs kind of come out of the page at you, and the hydrogens go into the page. So the lone pairs give the oxygen the partially negative side, and the hydrogens the partially positive side. This guy, water, is polar. Oh, that's not a very good P. Let's try that again. And then we're going to finally look at bromine. Bromine is diatomic. It's part of phenolphthalein, so it's Br2. And this guy is completely symmetrical. There's just 2 bromines. They have the exact same electronegativity. They have the same pull for the electrons in the bond. This is also nonpolar. So will CCl4 dissolve in water or bromine? It was going to dissolve in bromine. Why? Because bromine is nonpolar, just like CCl4 is, and they have induced dipole forces. So the next one. Which of the following molecules would be soluble in water and why? So again, since we're talking about structure effects, it's helpful to look at the structure of the molecules. Ki is ionic. I know it's ionic because potassium's a metal, iodine's a nonmetal. That gets together with large electronegativity differences. Remember that ionic dissolves in polar substances, and so this ionic potassium iodide will dissolve in water. And remember, especially group 1 salts are always soluble. So next we have CH3, CH2, CH3. That'll look something like this. CH3, CH2, CH3. We're going to put H's on all of those. And while I'm drawing this, hopefully you're looking at it and thinking that this guy looks completely symmetrical and totally nonpolar, which is what he is. Totally nonpolar. This will not dissolve in water. Next we have CH3NH2. And if you actually count up all the valence electrons and look and see, nitrogen needs to have a complete octet, and we need a couple more electrons anyway. So it should actually look something like that. So when you see that, hopefully what you're seeing is the hydrogen bonding. Let's go right there. There's an N and an H right there for hydrogen bonding. So let's say we put a water molecule here. Let's say we had an H2O. So we have hydrogen bonding that will exist between the N and the H of a water and the O and the H. So there's hydrogen bonding there. This guy is water soluble. And finally, for the last one, CH4, totally nonpolar, will not dissolve in water. One more example of structure effects. Which of the following vitamins would be the most soluble in water and why? So we've got vitamin C and K3 and A and B5. So let's look at vitamin C first. When I look at vitamin C, I see a whole lot of structures that look kind of like water, which means that they have hydrogen bonding and they would dissolve well in water. We have 4 spots for hydrogen bonding in this molecule. But if we look over at K3, I don't see any places for hydrogen bonding. Now remember that hydrogen bonding is H with N, O, or F. So something like CH3 does not count as hydrogen bonding because that's H with carbon, not H with nitrogen, oxygen, or fluorine. So there's no hydrogen bonds available here. For vitamin A, there is totally a place for hydrogen bonding. That's your polar part of your molecule. So we got polar over here. But just because there's a polar end, this entire rest of it is totally nonpolar. So the majority of the molecule is completely nonpolar. There's no way that's going to dissolve in water. And then finally for B5, I see an OH, an OH, an OH, and an NH. So there's again 4 spots for hydrogen bonding. So now we've got to look at these structures and pick which one's the most soluble in water. I can say automatically it's not vitamin A and it's not vitamin K3. But vitamin B5 and vitamin C both seem to be pretty soluble because they both have 4 sites for hydrogen bonding. So if I had to pick between them, I would pick vitamin C because the hydrogen bonds are kind of in a circle around the molecule, whereas on the vitamin B5 they all seem to be on one side. So you wouldn't get a whole lot of water attached down here at the bottom because there's really no hydrogen bonding sites available down here at the bottom. So if I had to guess, I'd pick vitamin C instead of vitamin B5, but I think that based on the structure, both of them would be pretty soluble. So now let's look at another factor that affects solubility. The next one is temperature effects. So we're going to start with gases. For gases, if you increase the temperature, then essentially what you're doing is increasing the kinetic energy. And so I'm going to have a container with water in it. And I'm going to put some oxygen molecules in it. So there's just little dots of oxygen molecules. So if I increase the temperature, I'm increasing the speed of the molecules. And for gases, that's going to make those molecules move much faster, but not just move faster, but be more likely to be able to escape from the container. So these molecules can move in any random direction, but the faster they move, the more likely that some of them at least are going to escape from the container. Well, if they escape from the container, then they're no longer dissolved in the liquid, and if they're no longer dissolved in the liquid, then we are decreasing the solubility. For gases, if you increase the temperature, you will decrease the solubility. So an example of this is thermal pollution. Let's say you have a lake with water in it, and fish swimming in the water. Remember that fish breathe oxygen that's dissolved in the water. So if there's oxygen dissolved in the water, let's make it purple, and a local power plant comes and dumps a whole bunch of hot water in the lake. So essentially they're making the lake hotter. Not dirty water, just hot water. But that's going to make those oxygen molecules move faster. And if those oxygen molecules move faster, then they could escape the lake. And so then the fish would have no oxygen to breathe because all the water oxygen escaped the lake, and the fish would drown. This is why if you're fishing on a really hot day, you're going to find most of the fish at the bottom of the lake because it's colder down there. But not really because it's colder, they're going to be at the bottom of the lake because there's more oxygen down there and it's easier for them to breathe. For solids and liquids, it's kind of the opposite. Usually if you increase temperature, you will increase solubility. And this doesn't happen with all solids and liquids. Some do one way and some do the other. But for the most part, solids and liquids increase in temperature will increase the solubility. If you make it hotter, a liquid is not going to escape from another liquid. Or if you make it hotter, sugar is not going to leap out of a glass of sweet tea. Sugar will still stay dissolved. And so making it hotter is essentially just allowing more of the intermolecular forces or more of the bonds to break. So if you had a glass of plain tea, unsweet tea, with little ice cubes in it, and you decided to put some sugar packets in it, most of the sugar would stay down at the bottom of your cup. And most of it wouldn't dissolve. If you bought unsweet tea and you sugared it yourself, most of the sugar would not dissolve. But when you buy sweet tea, the company who's making the sweet tea sugars it first while it's still hot. So if they put the sugar in it while the tea is still hot, then increasing the temperature is going to break the bonds, the intermolecular forces between the sugar molecules, and essentially all that sugar is going to dissolve, so you don't even see the sugar, and then they cool it down and put their little ice cubes in it, and it tastes a whole lot sweeter because they were able to sweeten it while it was still hot and then cool it down, which you can't do if you start with cold tea. So here's a graph that'll show you temperature effects on solubility. Notice that most of these lines head upwards, like most of these lines go in an upward direction. If it's going in an upward direction, that means that it is endothermic, going in an upward direction. Exothermic is going in a downward direction. And most of these lines go up. Most of these solids dissolve endothermically. And essentially what that means, endothermic dissolves better in hot water because endothermic has to take in heat and energy from the surroundings. So the hotter the water is, the hotter the surroundings are, the more energy there is to take in. Where exothermic dissolves better in cold because exothermic is giving heat off to the surroundings. So if the surroundings are already hot, they're not going to accept much heat. But if the surroundings are cold, they'll do much better. So something like PbNO32 has a really high solubility at a high temperature, say 65 degrees, but a really low solubility at a low temperature, say 0 degrees, so it dissolves better in hot. On this graph, you've got Na2SO4, which goes the opposite direction. It has a high solubility at a low temperature and a lower solubility at a high temperature. It dissolves better in cold. All right, the last factor that we're going to look at is pressure effects. This affects gases only. Solids and liquids cannot be compressed, so they don't really have any effect with pressure. Increasing the pressure of a gas over a liquid will increase the solubility of that gas. Here's the pressure effect. Increasing the pressure will increase the solubility of that gas. And that's actually Henry's law. The solubility of a gas is directly proportional to the pressure of the gas above the solution. We're going to talk about carbonated drinks. When you open a Coke can, you hear psst. And the reason why you're hearing that noise is because the gas is trying to escape from your Coke. When they bottle a Coke, they bottle it under really, really high pressure. So I have a can of Coke, and I'm going to put a whole bunch of pressure on it. And by putting a whole bunch of pressure on it when we bottle it, that'll keep, there's my liquid, that'll keep my gas dissolved within the Coke. But if I take my Coke home and I open it so that there's not very much pressure on it, and my liquid line's about the same place, now my gas is going to be able to escape, and the gas is going to be able to move around. So the more pressure I have on the soda, then the more oxygen or more carbon dioxide or more whatever you have dissolved into the soda. The less pressure, the less gas you have dissolved. So increasing the pressure will increase the solubility of the gas. All right, that's all I have for this time, and hopefully you'll join me again next time for methods of separation and other things about mixtures. See you then.